All right, this tutorial is on how to complete some of the problems from the practice problems on forces at an angle. So number 8 was one of the ones I was going to go over. So the first step is always going to be to draw the picture. So it says we have an object on an inclined plane. So there's our inclined plane. And then the angle is 15 degrees. And our object is right there. So you want to draw your free body diagram. So there's mg. There's our normal force. It says it's in equilibrium, so we don't have to worry about any forces up or down the plane. Additional forces, we just have the normal force and the force due to gravity. All right, so if you recall back to the video that we watched on solving for these kinds of problems, we want to set up our x and y so that they are lined up with the surface of the plane, because it simplifies the math a little bit. So what you want to do is you want to find the x and y components of the FG vector in terms of this new coordinate system, what I've shown in red. So if it's 15 degrees is what the angle of the inclined plane is, that works out to be that the angle between the force due to gravity vector and its y component is also 15 degrees. So if you want to find the y component of the gravitational vector, which is going to be equal in magnitude but opposite in direction to the normal force, it's going to be equal to mg, the magnitude of the total vector, times sine of theta. Nope. Times cosine of theta, excuse me, because we're talking about this particular vector. I'm going to erase that because it makes it kind of messy. So we have times cosine of theta. So put the numbers in. So the normal force is what we're solving for, is equal to the mass, which was 5.4 kilograms, times gravitational constant, 9.8 meters per second squared, times cosine of 15. So you do the math and you end up with that it is equal to 51.1 newtons is what the normal force is. Okay, so the next one, number 10, is an example problem, and this is a friction type problem. So just remember your coefficient of friction, mu, is equal to whatever the frictional force, either static or kinetic, divided by the normal force. So we said we have a 55 kilogram ice skater at rest on a flat skating rink. So the fact that it's flat tells us that our normal force and our force due to gravity are equal to each other. So we don't have to worry about the angles in this case. It says that you have to apply a 198 Newton horizontal force in order to get her moving. So that's how much force is required to break that static friction. So it tells you that your static friction is equal to 198 newtons. So if we want to find our coefficient of static friction, it'd be 198 newtons, the frictional force associated with the static friction, divided by the normal force, which is mg, and I'm going to come over here and I'm going to figure this out. Didn't leave myself enough space. So mg, mass is 55, g is 9.8, So your normal force ends up being, where'd it go? 539. So we're going to take our static friction and divide it by 539 newtons. And that gives us a coefficient of static friction that is equal to 0.37. Do the same thing. Now we're going to talk about the kinetic friction. It requires 175 newtons to keep it moving. So that's, but you don't have any acceleration at all. So that means that your applied force is exactly equal to your frictional force. So that means that our coefficient of kinetic friction is going to be 175 divided by the 539, the normal force. And it gives us a kinetic of, a coefficient of kinetic friction equal to 0.32. And sort of a good thing to check is that your static coefficient will always be larger than your kinetic coefficient, which is in this case. If you get the reverse, that probably means that you got the wrong number substituted in. All right, and the last one, this is a problem with many steps. So first let's draw the picture. So it says we have a 65 kilogram box sliding down a 37-degree ramp, and it has an acceleration, observed acceleration of 1.80 meters per second squared. And we want to find the coefficient of kinetic friction. All right, so let's draw our free body diagram. So there's force due to gravity, its weight. There's the normal force. Here is the sliding down the ramp. And it has an acceleration. So I'm going to put the net force in there. And then it also has friction, which is pulling backwards on it, slowing it down. So I'm going to do that like that. All right, so we know that the coefficient is going to be equal to the frictional force divided by the normal force. So first step, let's find the normal force. So normal force with these ramp problems is always mg cosine or whatever the angle is that they gave you. So the mass in this case is 65. G is 9.8. And then cosine of 37. So the normal force, we do the calculations, ends up being 509 newtons. Okay, so next thing we're ready to do is we're ready to set up our net force expression. So we have this one, which is directed in the same direction as the net force. I'll call that one Fg, because it's the force due to gravity lined along with the plane. And switch to blue, I guess. So we got our net force, this is what we actually observed happening, is equal to Fg minus the frictional force. So the net force is going to be equal to the mass of the object times the observed acceleration is equal to the force due to gravity, which is going to be mass of the object times g, and this is going to be the sine theta, because we're talking about this one, which is opposite to the angle, minus the frictional force. So if you solve this expression up here at the top, oh dear, in terms of the frictional force, you end up with that it is equal to mu k times, or the coefficient times the normal force. So let's substitute in some numbers. So 65 kilograms times the observed acceleration, which was 1.80, is equal to the mass of the object, 65 kilograms times gravitational constant times sine of 37 minus mu k, which is what we're looking for, times the normal force, which we already found, which is 509. All right, so I'm just going to fill in the numbers that you get when you do the math, because I didn't leave myself enough space. So you end up that the observed net force is 117 newtons, is equal to, and then the FG part of it was 383 newtons. Minus the coefficient times 509 newtons. So subtract 383 from both sides, and you get negative 266 newtons is equal to negative mu k times 509. Divide both sides by 509. And negative 509. Excuse me. And you get that your coefficient of kinetic friction in this case is 0.52. Now, the problem you actually have to do, I've changed the numbers, but the procedure is still going to be the same thing. All right, so the last part of that question, I'm going to use a new slide, is what acceleration would a 175 kilogram box have on this ramp? So let's just write out the variables first. So we have, starting with the equation, F net, that's what we observed, is equal to force due to gravity pulling it down the ramp minus the whole force of friction holding it back. So we have F net is equal to your mass times acceleration, which is equal to mass times gravity times sine of the angle. Friction is equal to, oh dear, mu times Fn. Fn is equal to mg cosine theta. So minus mu times mg cosine theta. Now, if you notice, we got mass in every single term. So the way this works out is that the acceleration is independent of the mass that is observed, that the mass of the object. So the acceleration would be the same as it was before. So the acceleration is still, why did I write that number down? 1.80 meters per second squared.